Okay, so welcome back. I was mentioning in the chat that I'd gotten a lot of questions about this particular homework via email, and so I just saw a bunch of them this morning right before class. So I'll respond to all those in the afternoon after my next class and after I eat. I'll respond to all of those. If you still have questions about it, don't worry about handing it in late. You can still ask me more questions on Friday, and maybe I'll even have like an office hour or something Friday if there's enough people that still haven't turned it in. So anyway, uh, we're now on lecture 30. Um, so what we did last time was we were discussing how a matrix can be viewed as a linear transformation under the right conditions in the opposite direction. You know, when you think of a linear transformation, maybe a matrix is the most natural thing that you should think of. Um, and so in this case, say we have a 2 by 2 matrix with real entries. This is a linear transformation. It satisfies both of the things that are required of linear transformations. And we had already seen how certain isometries of R2 are actually among linear transformations that are 2 by 2s, that are given by 2 by 2 matrices. So one is the following, right? Multiplying a point xy, so I think of xy as being a column vector, multiplying this column vector by this matrix, right, for appropriately chosen real numbers c and s, yields rotation. In fact, any rotation through the origin uh, can be done in this way. So rotation is not a problem here. Those are contained entirely in my group of 2 by 2 matrices like this. Reflection about lines passing through the origin are also fine. So the easiest example are the line passing through the origin that's just the x-axis. So reflecting the x-axis is easy. Reflecting the y-axis is similarly easy. It would just be -1, 0, 0, 1 here. So reflection in the coordinate axes is really easy, but we can combine rotation and reflection to yield reflection across any line that passes through the origin. So we saw this process last time. Here was what you do. So if you want to get reflection about any generic line passing through the origin, you first multiply by R inverse. Remember, we are restricting ourselves to the set of 2 by 2 matrices that have determinant that's non-zero. And the reason that we do that is because we know that isometries are invertible, right? So since isometries are invertible, I want these matrices to also be invertible, and that means I want their determinant to be non-zero. Okay. And so this process is the process that yields us reflection about a generic line L passing through the origin, but it doesn't yield us every reflection, right? So that might lead you to believe that we're headed in the right direction, that we can reflect about any line passed through the origin, because we know that any isometry is, a product of up to 3 reflections. But unfortunately, it doesn't. This is as good as we can do. We can't do better than this. And in fact, I showed an example last time of dilation, right? Dilation in the x direction, for instance. This is not an isometry, but it is an invertible matrix transformation, or an invertible linear transformation. Here's the main thing to note is that translations are not included in my linear transformation. So linear transformations do not include translations. And as I mentioned last time, the reason for this is simple. It's that linear transformations are forced by linearity to preserve the origin. Right? So this special nature of the origin must be preserved by a linear map. And here's the proof, here's the reason why. But this fails for a non-zero translation clearly because you move the origin, right? So the origin's clearly not preserved. Using translations, any point's the same as any other point. And we know that that's exactly what we want if you're talking about, geometry in the sense of Euclid, right? Euclid does not specify a special point that is somehow different from any other point in the plane. So we want to do away with this specialness of the origin. In order to do that, we would need to talk about what are called affine transformations. So affine transformations allow us to dispense with this specialness of the origin. Often you'll hear, so when I say affine geometry, what do I mean? Well, since we're in the Felix Klein world of geometry follows the transformations, right? Then affine geometry would be the study of the notions that are invariant under affine transformations. Well, I haven't defined what an affine transformation is, but before I do that, a lot of times the way that affine transformations are explained, kind of in a quick, casual way, is that affine transformations are like the normal Euclidean, or it's like linear transformations where you've forgotten the origin. Right, so it's kind of like doing affine geometry is kind of like doing Euclidean geometry, except you've just forgotten the origin. Or it's maybe I should say, rather than doing Euclidean geometry, it's affine geometry is more like think of the plane given to you from coordinates, or think of R2 as a vector space, but you've forgotten the origin, right? This is the notion of affine geometry. So I'll talk about that more a little bit in a second. But what is an affine transformation? So notice an arbitrary, it's a linear transformation of, say, R2. Of course, we don't have to talk about this in R2. We could talk about this in any space, but an arbitrary linear transformation I actually wrote it as R in there, but so an arbitrary linear transformation of R2, that takes a vector U, and we can think about this as it multiplies that vector U by some matrix M, and M is an A, B, C, D. And of course, if this thing has an inverse, then that's a special type of linear transformation, right? And that's where the isometries live, the ones that are included here. But then an affine transformation is a combination of a linear transformation and a translation. So an affine transformation is a combination of a linear transformation and a translation. And so the generic affine transformation might look like G of U, which is F of U plus some constant vector, right? I.e., this is like M times U plus a constant vector, right? Where C is a constant vector. Okay. Okay. Right. So, this is what a generic affine transformation looks like. Okay, it's of this form. Now, if we talk about affine transformations, you'll notice that, we now have, translations are now included here, right? In fact, what would a pure translation, be, for instance, from an affine transformation? Well, if I took M to be, say, the identity matrix, then M times U is just U, and so this would just be the vector U plus C, which would just be, a shift of that vector, by the constant vector C. Okay. So then, what is it that affine transformations preserve, right? So we already know what linear transformations preserve. What do affine transformations preserve? So, well, affine transformations, right? Shifting, right? Translations, I should say. That's all we're adding in here. Translations add what? Right? What do translations add? When I add in translations to the group of transformations that I'm thinking about, what is the only issue, right? If I add in more transformations, I have to worry about if those extra transformations preserve the same things, right? Well, translations preserve everything that I care about, right? They preserve straightness, they preserve length, they preserve angle, they preserve circularity. In fact, think about translation, right? Translation is just moving like this. They preserve everything except position, right? So position's the only thing that is not preserved. And so they preserve everything that linear transformations do, except position. Okay, and so affine transformations allow any point to become the origin, right? So note, affine transformations preserve everything linear transformations do, except the origin. Or I should say except position, so including the shifting of the origin. Okay. i.e., they allow any point to become the origin. Now, what's interesting, so what's interesting about this is that affine transformations are typically, this is where the statement "forgetting the origin," right, comes from. So affine geometry is like it's like you're looking at the plane, but you forgot where the origin is. Okay, or you're looking at your space, but you forgot where zero is. Okay. So then, there is a notion of affine geometry. So affine geometry is the study, right, of quantities invariant under affine transformations. What are quantities like this? Well, go back and look at the first few sections of chapter 4. All right, go back and look at the beginning of chapter 4. Okay, so what do we have if we do that? I actually can flip back to chapter 4 here. So remember, we had these theorems about, say, bisectors of parallelograms, and say like midpoints of, medians of triangles, basically, these midpoint and centroid theorems. Okay. So these are actually the types of things you would study under affine under affine geometry. One thing I should mention is a lot of times affine geometry is kind of classified as the study of like parallelism. That's That's one of the main things, because if you think about it, right, translations are included, and what's one of the like big things about translation? Well, translation of parallel lines, of course, preserves parallel lines, whereas say rotation, right, does also all the isometries preserve parallelism, but affine transformations are like I should say they're like a midpoint. So maybe that's actually the best way to say this. So affine geometry is like a middle ground between projective geometry and Euclidean geometry. Okay, and so what do I mean here? So these things kind of exist on a scale where here the notions are weaker and here the notions are stricter. Okay. So affine geometry is not as strict as Euclidean geometry, but it's stricter than projective geometry. Euclidean geometry is the strictest of these. It has the most rigid structure as a result of its, the isometries of R2 being the transformation groups we're talking about. So here, this is a nice way of thinking about this. I'll return to this at the end of this chapter, but this is kind of a nice thing to think of conceptually when you're thinking about the relationship between these geometries. Projective geometry is the weakest. It's the thing that has like the least notions, right? I mean, collinearity is all you have here, right? So anyway, this is a nice way of thinking about this. Okay, so moving on then, I want to return to our discussion of transformations of the projective line. So transformations of the projective line. So of course you can think about this as transformations of RP1. So remember previously we knew that these things looked like this, right? They were the linear fractional transformations, right? Where AD minus BC was not zero. So these are my linear fractional transformations, and we already proved why these were the things, right? We did this by showing that this is the general form of types of these transformations. So remember there were these three types. There was the type that was translation, right? So there was translation, and that was included by this. There was dilation, right, or scaling. So there's dilation. And then there was inversion, right? And so we proved, when we first talked about this at the end of chapter 5, that any transformation of the projective line was a combination of these. And, well, the general form of a combination of these things is a linear fractional transformation, AX plus B. Right? Now, of course, you see exactly what I'm going to say here. So note, if I let M be the matrix A, B, C, D, right, then these matrices behave an awful lot like these linear fractional transformations. So when we did this, we were actually working in the way that Felix Klein did when when Klein said that we start with the transformations and then see what things we're interested in based on what's invariant under the transformations. We did exactly that for RP1, right? So for RP1, we started with the transformations. We proved that the transformations had to look like this, and then we found quantities that these transformations preserved, right? So they preserved collinearity, and most importantly, they preserved the cross ratio, right? So this is exactly what we did. We started with the transformations, and then we found the things we were interested in from what these things fixed, right? And that was the cross ratio. And so, what do we say here? Well, to see where these come in, right? So if I let M be the matrix ABCD, we see that the fractional linear transformations behave an awful lot like linear transformations via, or by multiplying by M, just matrix multiplying. So we see that the fractional linear transformations are associated in some way, I'm going to put that in quotes, to linear transformations. So we'll see the nature of this association here in a second. Now, remember that we defined RP1 kind of differently before. So we defined RP2 in the usual way where we looked at space, right? And we thought of lines passing through the origin in space, and those were our points, right? And then the lines in RP2 were planes through the origin in normal space. Okay, so we could do the same thing with RP1. And so for RP1, you could say the points are lines through the origin in the plane, R2, right? So this is one way we could think about, oh, I'm off page there. So we could think of RP1 as a collection of points where our points are lines through the origin in R2, right? In the same way that we defined RP2 to be lines through the points are lines through the origin in R3. Okay, so if we do that, right, and we have actually, I believe we actually did this construction previously, but to see how this works, now here's a few lines through the origin in the plane, right? So here's the origin. Maybe I have a few lines like this. Okay. So think about the collection of all the lines passed through the origin in the plane, and those are going to be the points of RP1. But let's just pick out a single one of these. Okay. So let me redraw this. I'm going to pick out a single one, and I'm going to show that I can associate each line passing through the origin to some real number. Okay, so here's my origin, right? Here's the x-axis, here's the y-axis. Well, in my plane, there's the line y equals 1. Right. And for all but one line passing through the origin, right, every line except one passing through the origin has to intersect y equals 1, right? There's only a single line that is actually parallel, and their intersection happens out at infinity. Okay. And so this situation is the common one, right? So this situation is typical. So there is some intersection point. The only time there's not is when the line in question passing through the origin is the x-axis. So we'll talk about that later. Okay. So say that we have some point like this. Well, here's the origin. Here is 1. I have some distance here that is given to me by the x-coordinate of this point. Whatever this distance is, that is some real number s. And so I can assign to this line the real number s. Okay. All right, so if that x-coordinate is 10, right, then s is 10, and that line is associated to the number 10. Okay. All right. Now, here is what it would look like if I started labeling lines passing through the origin using that label S. Okay, so note as S gets bigger and bigger, these lines are getting more and more horizontal. We'll think about why that is here in a second. And of course, eventually I have this label of this horizontal line infinity, y. This horizontal line is the x-axis, and the x-axis doesn't intersect the line y equals 1. Well, it intersects it at infinity, so technically that distance s is infinite. Okay, or we can think of the x-coordinate of that point, right, would be some point not on the plane. All right, that point is not on the plane, and we call that point infinity. So 0 here is the x-coordinate of the line passing through y here, but this is just the y-axis, right? This is the map, or this is the association of the y-axis to the number 0. Okay. And similarly, here's the negative values of s. Okay, so in this way, associated every single line passing through the origin is some number. Okay. What is this number? Well, this coordinate, right, this is S1. Right, what is S? It is reciprocal slope. Right, it's run over rise. Why is it run over rise? Because S is the same as S over 1, but that is, you know, compared to the origin, right? This is S is the x coordinate, 1 is the y coordinate, so this is, you know, S minus 0 over 1 minus 0, sorry. So this is the reciprocal slope of that line, which also makes sense why we get these values that we do here. Okay. All right. Now, consider any projective map mapping the ordinary line y equals 1. Right? Any projective map of y equals 1 sends the point S1, right, to the point with x coordinate f of s, right, where f of s is exactly this fractional linear transformation as plus b over cs plus d. Right. So, I mean, this is just me mapping R2, sending the line with the label S to the line with the label AS plus B, or AS plus B over CS plus D. So this is, so then maybe I should write it like this. The line with label S gets sent to the line with label AS plus B over CS plus D. So, quotation marks, not parentheses. Okay. But what is the map? Right? What map does this? So what map sends the line with label S to the line with label AS plus B over CS plus D? Well, it's exactly that matrix transformation that we wrote out before. Right, the map, so a map that does this is multiplication by the matrix M, which is A, B, C, D. All right. So to see why that is, note that a line or a point on the line with label S can be written as SX, X, right? Where S is the label and then X is whatever. Okay. Well, how does my multiplication by M affect this column vector SX, X? Well, this is, if I just write out what column vector I get here, I get A SX plus B X, sorry. And in the second column, or in the second entry, I get CSX plus DX. Okay. Okay. But this, of course, represents, this column vector represents, maybe I'll just draw a line. So this represents, of course, the point ASX plus BX, CSX plus DX. Okay. And this lies on the line with reciprocal slope. I can just take the reciprocal slope, so rise, or run over rise, so ASX plus BX over CSX plus DX. But hey, X is in common here. I can factor it out and cancel it. And so this is AS plus B over CS plus D, i.e. the line with label AS plus B over CS plus D. And so we started with the line with label S. After multiplication by this matrix ABCD, I've sent my point to some point that lies on the line that has this reciprocal slope AS plus B over CS plus D. But that's how we determine the label of these lines. All right, we're labeling them by their reciprocal slope. Okay, and so it actually doesn't matter what the X is here, right? This map would do the same thing. And so this map maps the line with label S to the line with this label AS plus B over CS plus D. Okay. Now, what is the thing to note here? So note a point of RP1, right? So a point of RP1 is an entire line through the origin. Okay. This is important to remember because that's why we're talking about how this transformation defined by M sends lines to other lines, because I don't actually care how M moves the individual points. Thus, I care only what M does to entire lines not what it does to individual points. Individual points on those lines. This can be confusing when you're first looking at some of these examples and actually working them out. Okay, because unfortunately, it's not generally the case that it gets sent in a nice way. So here is a warning, i.e., consider the warning. It is not usually the case that the point S1 gets sent to the point AS plus B over CS plus D1. Okay. That's not usually what happens here. Example, consider inversion. Right, S getting sent to 1 over S. Right, it couldn't even happen there. Okay, so consider this inversion and the M associated to it. So it can't even happen here. This is a good example for you to work out if you are confused about how that's happening. Okay. So in fact, well, maybe I should say something here. I could say, well, exactly what happens is that when, for instance, you consider sending a point to its inverse point under this map, what does happen is the entire lines, right, represented by the labels 0 and infinity get mapped back and forth to one another, right? So, so note, right, M sends a point in R2 to another point in R2. Sometimes the same point, but, right? So M sends a point in R2 to another point in R2. Thus, what happens when we try to send the point, say, 1, 0 to the point 1 over 0, 1. Sorry, not 1, 0, 0, 1. 1, 0 is fine. So what happens when we try to send the point 0, 1 to the point 1 over 0, 1? Well, this is an issue because if I have an associated matrix here, how do I come up with a matrix that sends the point 0, 1 to 1 over 0, 1, or, you know, rewritten like this, infinity 1? Well, it can't, right? This isn't in R2. Right. Okay, so it can't even do that. But what can it do? So it can send the line with label 0 to the line with label infinity. So it can't send points to points. In fact, the solution, don't worry about the points. Don't worry about how M acts on points. So how does this solve my problem? M sends the line with label 0 to the line with label infinity. I.e., it sends the line, the y-axis to the x-axis, and vice versa. Okay. So this is a great example to show why it's easy to get bogged down if you try to can think of this thing point-wise. It's no good. Okay. All right. Also, another warning. Another warning. This representation of a fractional linear transformation, so this representation of a linear fractional transformation by M is not unique. So this representation is not unique. There's more than one way to do this. Why? Well, the answer is note that the two fractions as plus b over cs plus d and kas plus kb over kcs plus kd, where k is not 0, are equal. Right? And so, if my associated matrix on the left is A, B, C, D, my associated matrix on the right, of course, is K times M, which is KA, KB, KC, and KD. Right? And so dilations of that matrix are perfectly fine. Okay. So the linear transformations Km combine the transformation M with dilation by this factor K. So they're all different, right? You pick any two different values of K here, right? And K is not allowed to be 0. So you pick K equals 2 and K equals 3. Those are two different matrices or two different transformations, M, but they represent the same linear fractional transformation. Okay. So again, we care about how it treats lines, right? Because it very much, two different choices of K very much sends individual points to different points, but it sends lines to entire lines. So that's why we're fine here. Okay. All right. So this chapter can be a little bit tough to wrap your mind around because it's kind of rapid fire. Like I'm just kind of throwing out a bunch of different stuff here to illustrate a bunch of different ideas. And so you shouldn't view this as, it's not a normal like progression of things. This is just I'm just throwing in some things here and there to illustrate what it is that's going on here. Okay. So that's that. So now for something totally different, right? So now for something completely different. So now for something different. Okay, but this is something that is a very important example of illustrating these same concepts. It's spherical geometry. Okay, it is doing geometry on a sphere. So, for instance, let me get a good, nice picture here, right? Something like this. Right, here's a very nice picture of doing stuff on the sphere. Right, there we go. Okay, you might have seen a lot of diagrams like this before. And inherently, from other topics, right, other than geometry or math, a lot of things about the sphere. The first thing that should be noted, this was actually an ancient example of non-Euclidean geometry. So this is actually an ancient example of non-Euclidean geometry. So then why is it not going to be the premier example of non-Euclidean geometry that we're building up to, right? This entire course is building up to hyperbolic geometry, which is a great example of non-Euclidean geometry. But why is it that I'm going to focus on that as my example of non-Euclidean geometry? And that's what I'm going to devote all the time to. When we have non-Euclidean geometry here, clearly like seeable on the sphere as spherical geometry, mathematicians for many, many years understood spherical geometry and understood that the concepts were similar in a lot of ways to Euclidean geometry, but there were several things that were just totally different and failed fundamental Euclidean geometry facts. So what is it that's going on here? So maybe I should write here because I'm going to talk for a bit and I'm not going to write it all out because it would take forever. So then the question is, why didn't the ancients, nor many of the pre-19th century moderns, consider this non-Euclidean? So here's the big question. What was the deal? Why didn't they consider this to be non-Euclidean? They didn't consider it like a legit example of non-Euclidean geometry. Why is that? There's a lot of complicated things that go into this. And unfortunately, to see the full answer to some of the things I'm going to talk about is essentially like an entire semester-long course. It's Geometry 436, or Math 436, which is differential geometry. So Math 436 is differential geometry, and you will eventually, in differential geometry, prove a theorem called the Theorema Aggregium that was proven by Gauss. That's Latin for remarkable theorem. And basically, it's because they didn't understand the remarkable theorem that they didn't consider this non-Euclidean. So what am I talking about? I haven't even said why this is non-Euclidean yet. So let's go back to this picture. Okay. So on a sphere, I have stuff drawn here, right? What are those? What are those things that are drawn? L, M, and N. Those are great circles, okay, on the sphere. What is a great circle? If you're thinking about this sphere sitting in space, and its center's at the origin, we'll say, right? Even if you have a sphere sitting in space and it's not, we know that we can move it there, and that's fine, right? In Euclidean geometry, I can shift things around like that. That's just a translation. So I have sphere sitting at the origin, so its center's the origin. Okay, so I have a sphere sitting in that way. Well, what is a great circle on this sphere? A great circle is the intersection of a plane passing through the center of the sphere, in this case the origin, and the sphere itself, right? So if you think of a plane cutting through the sphere, a plane, passing through the origin, that is the center of the sphere, cutting it, these are the cut marks, okay? Those are great circles. Now, why am I talking about great circles? Because it has been understood for a very long time that if I want to talk about the shortest distance between 2 points on a sphere, well, I can't just use the Euclidean straight line, say, from P to Q, because that line is inside the sphere. I'm not allowed to do that, right? I'm a little ant that is restricted to the surface here, because the sphere, when we say sphere, we mean the surface of this ball, right? Not the inside. The inside doesn't exist. So if I'm a little ant living on this surface, I can't dig, so I can't go into the sphere. I can't jump. I can't go off the sphere. The only thing that exists for me are 2 directions on the sphere, and that's why the sphere is a 2-dimensional thing. Okay. And so if I'm a little creature living on this sphere, the shortest distance from P to Q for me, I can't use the Euclidean straight line to go there. I have to walk along an arc of a great circle. Okay. And so what does that mean? It means that the lines in spherical geometry are arcs of great circles. Why? Well, you can't have actual lines. In fact, right, if you have 2 points on a sphere, you draw the line between them. The sphere is convex, so that line is inside the sphere, i.e., that line is definitely not on the sphere. So any Euclidean line connecting any 2 points on the sphere is not even on the sphere itself, right? No point of it except the endpoints are on the sphere. So I can't even talk about Euclidean lines on a sphere. I can only talk about something else, right? And great circles are that thing. Well, when I have lines that look as wacky as great circles do, they behave a lot wackier than the lines that I'm used to from Euclidean geometry. One of the things is that two great circles, right, always intersect. So there's no such thing as parallel lines on the sphere, right? Any lines intersect, and so that automatically means it fails the parallel postulate, because the answer, how many parallel lines can I draw to a given parallel line through a point that's not on it? Zero, right? Not one, not infinitely many, zero, right? Alternatively, it fails even the Pythagorean theorem. So I'll talk about that more last time. I've run out of time here. I'll start here next time, and then we'll be after I talk about the sphere, and I might bring in the quaternions just because it's neat to talk about. But after we mention some spherical geometry, I am going to jump to chapter 8, and I may return to the last half of chapter 7 later, because it's interesting, but we're not going to need it for what we do in chapter 8. And so next time on Friday, I'll talk about spherical geometry. So anyway, so that is it. Like I said, don't worry about the homework. If you are still not finished tonight, don't worry. You can talk to me on Friday if my answers to your questions by email are not are not good enough to do it. We can talk about it some on Friday. I can even devote 10-15 minutes to class on Friday to talk about it. So yeah, don't worry about the homework. So anyway, I will see you all on Friday.